Alright, welcome to the 14th week of our artificial intelligence lecture. Today we will be discussing introduction to transfer learning for deep learning. That's one of the most interesting topics in deep learning. So we will start with an intuition for transfer learning. We will see what transfer learning is, how we can make use of it, and then we will have a hands-on example for training Resnet with CIFAR data. So what is transfer learning actually? If you can play guitar, it's usually easier to learn playing banjo because they're both instruments with strings. They have similar note and chord structure, and if you can play the guitar, then you know something about music theory. So basically the idea behind transfer learning is if you can do something, that means it's easier to do something else that's almost similar to that task. So transfer learning is a research problem in machine learning that focuses on applying knowledge gained while solving one task to a related task. For example, knowledge gained while learning to recognize cars could be applied when training to recognize trucks. Reusing transferring information from previously learned tasks to new tasks has the potential to significantly improve learning efficiency. So again, the same example. You need to spend years for learning how to play guitar. You need to strengthen your fingers, you need to understand the chord structure. But once you understand how you can play the guitar, then you can transfer this knowledge to playing something else like the banjo. That's the same with the transfer learning in neural networks. If you already have a network that you use for something, for example, recognizing cars, then you can make use of this network to, for example, recognize trucks. So it's the problem of either learning from scratch or building on top of a previously learned things. Think about a baby. A baby learns from scratch, and you know how much time it takes for a baby to understand stuff. It usually takes like 10 years for a human being to understand most of the things. But let's say if we work like the people in Matrix, for example, and if you get a pill that basically transfers you some knowledge, then your learning process is much easier. You don't need like 10 years to learn, for example, calculus or some basic mathematics. That's the idea behind transfer learning. So make use of previously learned stuff. Just don't start from scratch. So why do we basically need transfer learning? So we usually use very deep networks that are very difficult to train and requires amazing amount of data. Up until now, we usually worked with stuff like LeNet, which is kind of a humble neural network. It's not very complicated, and it was kind of easy to train that kind of network. But today we will see, for example, Resnet, which is a very deep network, and you will see it's difficult to design a network, something like that. It's very difficult to train a network like that. You need a lot of data, you need hardware. So it's basically almost impossible to start from scratch if you will be building a very complicated network. If you are an individual researcher, it's highly unlikely that you come up with a model that can beat the work of a big research group. That's unfortunately true. Even if you are the most genius person in the world, you won't have the hardware to beat that. You won't have the data to beat that. So it's always a good idea to build on top of something else. Okay. And even if you are the greatest, you can become greater if you rise on top of a giant's shoulder. So that's what Isaac Newton said. If I have seen further than others, it's by standing upon the shoulders of giants. So if you basically stand upon the shoulders of giants, I mean, if you use the knowledge, existing knowledge, then you can make it better. So that's the whole idea behind transfer learning. Just make use of the knowledge from someone else's network or someone else's work. Okay. So this is basically the network structure of LANet, for example. That's kind of the network we usually used up until now. We have an input image. We first have the convolutional layers, and then we have some pooling layers. We have convolutional layers as well. Then we have fully connected layers, and then we make the decision. This can solve a lot of problems. No problem with that. But this is a very humble network. You cannot go so further with this kind of network. If you increase the number of classes, then you will see that's not gonna work in a good way. So you need to have much complicated networks, such as this one. So this is the architecture of Resnet that's developed by Microsoft. And this is basically the Resnet50, the network we will be using for today's lecture. As you see, there are really a lot of layers. I mean, this is a basic drawing. There are much layers than what you see here. So it's basically, that's a very advanced network that requires a lot of data for training. You cannot just use a couple of hundred of images to train for this network. That's not gonna happen. That's too deep for that. And its initial layers are mostly responsible from visual features learning. So as you see, it basically makes a classification decision. That's what Resnet does. But most of the layers, apart from the last layers, they are basically responsible from visual feature learning. So you can just use that features, you can just use that layers, because their task is basically learning good features that can discriminate things. Okay, so why we don't you just use these layers in order to get better results for our own tasks? So since it's trained for millions of images, the visual features are really powerful. I mean, we will see the database we use to train ResNet. It contains 40 million images. As an individual researcher, you will never ever be able to find that many images. You cannot even download that many images. So they are labeled images. That's very powerful. And the network is trained with that images. And trust me, training a network is not that easy as well. So you have a very powerful network. Why not to use that network for other tasks? So that's what we will be doing with transfer learning. Just to visualize the stuff, this is our humble LearnNet architecture with convolutional layers and pooling layers and flattening and other stuff. This looks like very humble when you compare this super huge network. This is the visualization of Resnet architecture. You see, that's even impossible to check basically all the layers for that network. So if you can use the knowledge that's compressed in this network, that's great. And that's what we basically do with the transfer learning. We will be using the knowledge, the visual feature detection knowledge that's compressed in this network. So if you have such a complex architecture, you need a lot of data for training. That's one thing. The deeper your network goes, the more images you need for training. And that's where image databases such as ImageNet comes into play. So if you go to this site, you can basically get the images for yourself if you're interested. So the day I basically visited that site, the database contains 14 million images. 14 million images. So the ImageNet project is a large visual database designed for use in visual object cognition software research. More than 14 million images have been hand annotated by the project to indicate what objects are pictured, and in at least 1 million of the images, bounding boxes are also provided. So if you're interested in object localization or object segmentation, you can still use this database as well. It's not just for classification. So ImageNet contains more than 20,000 categories, with a typical category such as balloon or strawberry consisting of several hundred images. So it has quite a few categories. It can solve many problems, but that doesn't mean it can solve basically your problem. You might be interested in something totally else, or you might be wishing to squeeze this network. So you may want to just make decisions for just two classes. You wouldn't need 20,000 categories. You may need just two categories. So once we modify this network, then that's transfer learning. We will be just using some parts of the network, and the rest we will be adding. So why people created a network? Why people created a database like ImageNet? So AI researcher Li Feifei began working on the idea for ImageNet in 2006. At a time when most AI research focused on models and algorithms, Li wanted to expand and improve the data available to train AI algorithms. And this was a very wise decision, actually, because even if your model is great, if you cannot train it with a lot of data, then your performance will not be good. So that's something we have discussed in the previous lectures. If you basically have a big network, then you need a lot of data for training. And if you feed your network with more data, your performance increases. So that's what Lee basically found out, and she created this ImageNet database. So on September 2012, a convolutional neural network called AlexNet achieved a top 5 error rate of 15% in the ImageNet challenge in 2012, more than 10 percent points lower than that of the runner-up. So that's a milestone in image processing and in deep learning, basically. 2012. That is basically a milestone. So this was made feasible due to the use of graphic processing units (GPUs) during training, an essential ingredient of the deep learning revolution. And that was basically possible because they used GPUs for training and they basically used a lot of data. And that showed if you have a complex enough network and if you have a lot of data, you can basically solve a lot of problems. And 10% difference between the second coming algorithm, this is huge. So this was very successful. And 2012 showed us deep learning is basically working, and it's actually pretty strong if you can train it with good data. So for today's lecture, what we will be doing is we will basically take Resnet, which was trained in ImageNet with 40 million images, and then we will use the visual features of Resnet to train for two classes from another database called CIFAR. So CIFAR dataset, that's another image dataset, consists of 60,000 images. They are 32 by 32 color images. So they are RGB images, 30 by 32 by 32. They are very, very small, tiny images actually. And we have 10 classes with 6,000 images per class. And there are 50,000 training images and 10,000 test images. We will be just using a very small subset that I provided in the video link. We will be using dog images and horse images. We will use the visual features of Resnet, and then we will create another network on top of Resnet's visual features to classify between dogs and horses. So I already provided you the dog and horse images that we will be using for the practical example, hands-on example. But you can basically extract data from CIFAR, or you can just find out other images for the problem you would like to solve. And if you use the same directory structure, you can just load them and then you can make use of them to solve your problem. Okay, as usual, we will be importing TensorFlow, Pandas, NumPy, Matplotlib, Seaborn, and random. So that's basically the initialization phase, importing phase. And then these commands will basically download Resnet50 from internet. But this is Resnet50 trained with ImageNet. So this ResNet is basically trained with these 14 million images. Okay. Um, Once you do that, you can basically save it to your hard drive if your internet connection is not good enough. You don't need to download it over and over again. If you just save it to the hard drive, that's like 150 megabytes for now. You can reuse it by loading the model. So let's see what problems we can basically solve with this ResNet network. We will be just using to make predictions. I will be loading a bicycle image, okay, from my hard drive, which is inside a folder called Packit. That's the image I will be using. You see, we have something called the target size here. That's 224 by 224. That's because ResNet, as it is using an image dimension of 224 by 224. Okay, that's important to remember. Even if your image is smaller, as our images will be doing, you need to convert your image size, your target image size to 224 by 224. That's one thing you should definitely remember. So we loaded our image, and if you take a look at the image, that's a bicycle image. That's not even a real bicycle actually, but this is a bicycle image. So we need to do some stuff in order to use that image for prediction on ResNet. So let's see what we need to do. First of all, we need to convert our image to array. And then we need to expand the dimensions. So when you take a look at the dimensions of this image, that's 224 by 224 by 3. Okay. But if you remember from our previous lectures, in order to make predictions, and if our model is using batches, then we need to basically input a tensor which has 4 dimensions. The first dimension is the batch size, the second dimension is the width, then the third is height, and the fourth is the number of layers. Therefore, we basically need an image which have a shape of 1, 2, 2, 4, 2, 2, 4, 3. So if you load the image as it is, that's the dimension you will have. Okay, but if you basically use this command to expand the dimensions from 3 to 4, then you will have basically these dimensions. Okay, that's the batch size, width, height, and that's the number of layers. Since this is an RGB image, that's a colored image, that's 3, that's the width, that's the height, and that's the batch size, since we will be inputting just one image. Okay, so now there is one thing else we need to do in order to input this image to ResNet. And you can basically perform this with Keras's Resnet50 preprocess input command. Okay, that's basically going to scale your image. So if you remember, either our network should have image pixels from 0 to 1 or -1 to 1 or 0 to 255. It's not easy to know that beforehand. Okay, and it's usually a better idea for the network creators to supply a function something like this, so that it basically converts an ordinary image whose pixels are from 0 to 255 to whatever scale it uses. Okay, and once we do that, then the scaling operation is over as well. Then we can make the prediction with our predict function. So it takes a little bit time, and then if you would like to see the result of the prediction, since we have thousands of classes in ResNet, we are just interested in top 10 predictions. Okay, that will give us the label as well as the classification probability for the top 10 predictions. And as you see, the first prediction is mountain bike with a very high probability, that's 0.7. And basically the second possible option is bicycle build for 2, which has a probability of 0.16, which is not bad as well. And the third prediction is a tricycle that has a significantly lower probability, and the rest is usually you don't need to care about the rest. I mean, these are very low probabilities. The highest probability, which has a very high gap between the second highest, is the mountain bike, which means our network basically predicted this as a mountain bike. Okay, so the network is basically working. So what we just did is we basically loaded ResNet from internet, okay, and then we prepared an image as an input. We just downloaded a JPEG image. We loaded this with Keras and Tensorflow. We basically made the pre-processing so that the image is ready for the network. And then we basically use the prediction commands from TensorFlow to make the prediction for our own image. And we basically found out that's a mountain bike. So this is as easy as it is. I mean, you just use other people's network. But what if we would like to solve another problem with that network? Now let's take a look at what basically ResNet looks like. If you remember visual keras from our previous lectures, you can just say visual keras layered view. You just provide the model, and then that's it. You can just visualize that model. Okay, and in this case, you see that's a very crowded network. But one thing we need to understand is most of the parts of this network is basically responsible from learning visual features. That's almost all of the layers apart from the top layers of the network. They are responsible from learning visual features. So if I can basically use that parts as they are, I can basically solve other problems. So I would like to, for example, for this example, solve the problem of discriminating between dogs and horses. That's the problem I would like to solve. I'm not interested in mountain bikes, I'm not interested in cars or trucks. I would like to just solve the problem of discriminating between dogs and horses. That's the problem I would like to solve. But I don't have too many images. And I would like to use the visual features from Resnet50 because that's a network trained with 14 million images. So its visual features are really powerful. And since it is so deep, if you take a look at, for example, model.summary, you can see this network is huge. Really. If I would like to train this, that would take ages, and most probably my hardware is not suitable even for that. And as you see, it has 25 million trainable parameters. This is huge. This is really huge. And you see most of the prediction stuff is done here. These are just a couple of layers that are making the prediction. The rest is basically there for learning visual features. Okay. So how can I make use of ImageNet's visual features? So here comes the transfer learning part of our lecture. So first of all, we will get the Resnet50 from internet as well, but this time instead of just saying weights are coming from ImageNet, we have this parameter, include top false. This means basically get every weight for the Resnet50, but you don't need to get the top layers, which is responsible from the classification parts. We will be just getting the part that is responsible from visual features, and we call this as the base model. Okay, and if you take a look at the summary of base model, remember this says the bare model has 25 million parameters, the one with top layers as well, and the one we just requested, which doesn't include the top layers, it has just 23 million parameters, as you see. It's 2 million parameters less than the network above. So this is the full network. Okay, this is the full ResNet network, and this basically is the network with only visual features. It doesn't have the top layer, which is responsible from the classification. Now I need to create another network part that I will be connecting on top of this base network so that it can make classification. And this is how I do it. Okay. Now that I am basically done here with a tensor, I first need to have an average pooling. That's basically a pooling mechanism as well. That's like max pooling. This is global average pooling. That's a layer to basically make or compress the knowledge from the last layer of our base network. So here I basically compressed the knowledge. Then I added one dense layer with an activation function redo. Then I added another dense layer, and another dense layer. They all have 124 neurons inside. Then I added another dense layer which has less neurons. And then I added my last layer with 2 neurons because I would like to solve the problem of discriminating between dogs and horses. Okay, I just have 2 classes. I don't have 12 million or 20 million, 20,000 classes. I just have 2 classes, so I will just add 2 neurons here at the very last layer. Okay. And the way I create my model is basically you just say inputs are coming from base models input layers and outputs are coming from this network called I called as preds, which is basically the combination of these layers. Okay. So my final network has 2 parts. The first part is basically coming from ResNet's visual features, and the last part of my network is coming from here, where I defined average pooling, 4 dense layers, and a last layer with 2 neurons. Okay, this is basically it. I mean, this is just how you define your transfer learning network. So when you take a look at our last model that we created now, what we have is actually a network with 28 million parameters. That's even higher than the network, original Resnet50 network. It was 25 million parameters. We cut it, the top layers of Resnet. We obtained 23 million parameters. Now we have 28 million parameters because we added a lot of dense layers with 1024 neurons. So this is basically how we defined our network. These are the layers we added. Okay, so this is the global average pooling layer. So this is where ResNet finished its work. Okay, so this is the last tensor coming from ResNet. That's where the visual features end. And these guys are the layers we added. The average pooling layer, the first dense layer with 1024 neurons, the second dense layer, third dense layer, fourth dense layer with 512 neurons, and the last dense layer which have 2 neurons. Okay, this is basically what we have or what we added to Resnet50. So another thing we need to do is now we have basically a lot of layers, but the first 175 layers are coming from ResNet, and I don't want to change them. I don't want to train them again because I don't have too many images. I have a couple of hundreds of images for dogs and horses. So I just would like to use the layers coming from ResNet as they are. I don't want to train their weights. I don't want to predict their biases. I will just use that network as it is. Okay, that's the idea behind transfer learning actually. You don't train that network. That's one strategy. Or if you would like to really train that network, if you believe you have a lot of data, and if you would like to train that network, you just change that layer slowly. You don't train them normal. Okay. The second strategy for transfer learning is you just train them slowly, that layer slowly. Or the mostly used strategy is you just freeze that layers by just saying that layers are not trainable by assigning them trainable false. You freeze that layers, and during the training phase, neither weights nor the biases changes for that layers. Okay. And we specifically says the layers after 175, which are the layers I just added to the network, these are trainable. During the training phase, please train them. Okay. So this is basically how we define which layers are trainable for our newly created network and which layers are not trainable. Now I need to prepare my data. So what I did for this project is I basically got some images from CIFAR for two categories, for dogs and horses. And as you see, the images are really tiny. I mean, this is supposed to be a dog image, as well as these are dog images. So it's basically pretty difficult for the network to understand this is a dog, because ResNet is basically trained with proper images. CIFAR images are too small. That's 32 by 32. That's ultra tiny. And these are basically horse images from CIFAR as well. You see, that's very challenging problem. But I guarantee you is the visual features we will be using are so powerful and they are coming from ResNet. So it should be solving that problem. So you can basically gather your own images. One thing you need to be careful about is the naming of the images. You see, for example, this is the category name, that's the zeroed image.jpg. You need to have a folder structure. You need to have all your classes in one folder, and for each class, you need to have one folder. If you prepare a folder structure like that, you can train your own images as well, or you can give it a try with the images I provided you. Okay. So this is basically defining a training data generator, and then here we say we will be using the images inside the images folder. I would like to have them 224 by 224. Remember, they are pretty small images. They are 32 by 32 images. It's gonna upscale automatically all the images to 224 by 224. It says they are basically RGB images with 3 layers, and we will be using page size of 32, and in each training epoch we will be using 32 images. That's saying it's a categorical classification problem, and then we say for inside each epoch we will shuffle the images. Okay, and once you basically run this command, it says I found this number of images belonging to two classes, because inside our image folder, as you see, we have two classes, okay, dogs and horses. So the definition of our network is ready. The inputs for our network training is ready here. Now we need to define the optimizer as well as the loss function for our network. And the optimizer is the Adam optimizer. We will be using categorical cross entropy as the loss. And with this command, you can basically train your network. Now, one thing I would like to show you is, if you remember from our previous examples, we had quite a lot of epochs. Right now we have, for example, 8 epochs. You can increase or decrease this number by yourself. But if you take a look at the training history, we start with a loss of 0.5 and with an accuracy of 0.7. This could be lower or higher, that doesn't really matter. But as you see, with even 8 epochs, the accuracy increases dramatically and the loss is decreasing dramatically, which means our basically features, visual features coming from ResNet is working pretty good. And since the images from CIFAR is too small, that is basically not a very big problem. So we made a huge network. We make use of a huge network, Resnet50, and we basically solved a small problem, which is dealing with classifying dogs and horses. And we could just create a new network with 8 epochs. Usually that's not possible since we are basically building on top of another network that was possible. Okay. So this is a function I provided you guys to make predictions with our newly generated model. We basically make a prediction with dog image, horse image, and dog image. Let me show you that images. So this is the dog image I will be using to make the prediction. So remember, we basically trained our network with 32 by 32 tiny dog images. And this is a huge image. It's gonna be scaled to 224 by 224, but in the end, as you see, the model basically made a prediction that's praising the dog class. If the first number is higher, that means our network is classifying this as a dog. If the second number is higher, then our network is classifying this as a horse. Okay, so our network could classify that dog image correctly. Now let's take a look at our horse image. You see that's the horse we will be providing to the network. If you take a look at the probabilities, our network is almost certain that this is a dog, this is a horse, because the second probability is higher than the first probability. And let's take a look at the second dog image. You see that's another dog we will be using for the prediction. And as you see, our network is quite certain that this is a dog because the first probability is higher than the second probability. So you can basically save that model by using save command of Tensorflow, and then you can load that model basically, and then you can use the make prediction function in order to see whether you will be getting the same results or not. So what we did is we basically loaded Resnet50 that was trained with ImageNet. We neglected its top layers, which are responsible from classification problem, and then we added our own dense layers to solve a very simple classification problem, which is trying to classify images of dogs and horses. So if you would like to solve other problems with CIFAR database, that's basically the code you need to use. You can just download CIFAR 10 batches, and then from any batch you can basically select the categories you would like to solve. You can actually increase the number of categories. We just use dogs and horses. You can just use other animals, dogs, cats, and horses, for example. You can change a lot of things. Please try to understand how things work with transfer learning by changing our inputs, by changing our datasets. But the basic idea is you just make use of an existing network. On top of that existing network, you add some other layers, and then you can use this newly created layer for training, for solving another problem. In this case, we used our newly created network for solving the problem of classifying dogs and horses. And since we started with a very good network, which is Resnet50, we didn't need a lot of epochs. With even 5 epochs, we could actually get very good results. As you see in the fifth epoch, the accuracy is quite high. You don't even need 8 epochs. You can just have 5 epochs, 6 epochs. That should do the job as well. Okay, so that was basically it for transfer learning. Just to summarize, the idea is using other people's networks to create better networks or solve other problems. So transferring knowledge from one domain to another domain. That's the problem we are solving with transfer learning.